In the last lecture, we discussed about acceptance sampling. In this 14th lecture, I will tell about control charts. So, it is a part of statistical process control. Statistical process control is a concept to solve the problems of quality control. The much credit for applying concepts of statistics to problems of quality control to Walter Seward, who is a much senior person. Even Deming got inspiration from Seward. Seward invented the control chart to reduce variability in the performance of telephones at Bell laboratories. Edward Deming recognized the usefulness of these concepts in manufacturing and even in non-manufacturing sector. So, first I want to tell something about on-line and off-line quality control. If quality improvement can be attained during the process of production, the technique is called on-line quality control, and this control chart helps in on-line quality control. And off-line quality control refers to the techniques used before the actual process of production starts. Quality is thus built into the product and process as early as at the design stage. Mostly it was propagated by Taguchi. Even at design stage you make it perfect. This approach eliminates the need for mass inspection, that is a wasteful activity. In the manufacturing industry, off-line quality control is incorporated through experimental design methods or design of experiments methods. You know what is the effect of what parameter, in what way things will change. Considering that even random variation at design stage, that means your product itself should be robust enough that if there will be some fluctuation in temperature etc., then product will not deviate in the performance too much. So, that means you have to make design itself robust so that there is not much quality problem. Like design itself is such a good that minor manufacturing errors will not reduce its performance. So, Professor Junichi Taguchi of Japan pioneered this method, also called Taguchi method. It ensures good performance of products or processes by identifying and controlling the factors that contribute to variation. So, systematic way he identifies that what are the parameters which affect, say let us say what is the effect of temperature, what is the effect of humidity, like that. So, this is off-line quality, but here I am going to discuss more about on-line quality control. So, this type of some fluctuations are there because there is a randomness. Let us say that we talk about assignable and random causes. Let us say that some delivery boy is there and he makes the trips, he supplies this thing, and you are noting down the delivery time. So, delivery time keeps fluctuating, okay. It may be in terms of the minute to same destination, from office to same destination. Sometimes it took say something like 85, maybe average is your 85 or 86, whatever this line comes, but there are random fluctuations. So, some fluctuations will be very small. They are called random causes. You cannot know that what is the reason. There may not be any major phenomena. Slightly that person has become slow, he stopped doing that something at a very slow speed, or he may be having slight cold and cough, on the way he stopped a bit, that type of thing, many things. But there if the variation is too much, that means it is not a random cause, it is assignable cause. That means you can assign some reason to that. Say for example, one day delivery boy took about 100 minutes. Which is normal time is T5. So, that what happens? So, there was some accidents on the motorway, some accident was there and there was some traffic problem. Another day also it took more time, some day, then that time there was tire puncture. So, there is some assignable reason. Then here stopped by police for speeding one day. So, you know that you have got assignable cause here. And here you have got sometimes we saw that okay, he came much earlier. So, maybe the delivery was done that day by helicopter, and here express delivery maybe by some other this one. So, these are the assignable reasons. So, there are two causes random causes which cannot be identified properly, that you cannot know what are the causes, and assignable causes. Okay. Now, for making the control chart, we have to understand one central limit theorem. We know many times, as we have already told, that the process is normally distributed, most of the natural process. That means, suppose I am giving my lecture, so sometimes I am trying to keep my mean as 30. Okay. If I try to keep my mean as 30 minutes, that my each lecture will be 30 minutes, then sometimes I am taking more and sometimes I am taking less time also. But as that chance is there, but the chance more you deviate from the mean, chance keeps reducing a bit. That means it is very likely that okay, I can take maybe 35 minutes and or 25 minutes, but it is very unlikely that I will take even 40 minutes. Okay. So, this type of distribution is there, but it is not always that you have normal distribution also only. Sometimes you may have uniform distribution also. So, the central limit theorem states that irrespective of the distribution of the individual readings, be it uniform, be it exponential, be it any other thing, the sample means are normally distributed with the same mean but narrower standard deviations than that of individual readings. This I have told in lecture, not in the previous lecture, but one lecture before the previous lecture. That is central limit theorem. So, the distribution of sample means from any population tends to a normal distribution as the sample size tends to infinity. The normal distribution has a variability given by standard deviation. The variability in the sample distribution is given by standard error and related to sigma by the relation sigma x is equal to sigma by under root n. So, sigma is the population standard deviation. This is population distribution standard deviation SD, and this is your sample mean. Okay. SD of sample mean. Okay. Sample mean. Okay. So, that means it becomes sigma by under root n. So, like I am giving the example here, it is so important theorem that although I have spoken in one of the previous lectures, but still I am explaining again. Suppose you have got histogram of population, that there is some quantity that it may be anything that 0 to 10. Okay. Suppose chances that there will be, say, let us say 10 defect is equal, 9 defect equal, like that. Suppose you have got a uniform type of distribution, but if you take two samples and take the mean of them, you will be surprised that even by 2 samples, the things will become, that mean will become normally distributed type of thing. Because when you take in a random basis, maybe you can take sometimes very high value, then another can come low value. But if you increase that n is equal to 10, that sample size is 10, then it will be even more normal, and if you take n is equal to 50, it will be even more normal, and even variability will also be less. That means it smoothens out. Okay. So, that type of thing is there. So, based on that concept, if I want to make control chart for variable quantity, what I can do, that I can plot the mean of that sample, I can plot the sample mean. Instead of plotting the quantity, I must plot the mean, and this is minus 3 sigma by under root n, that is standard error, that is standard deviation of the sample mean is sigma by under root n. So, minus 3 sigma and plus 3 sigma. So, up to plus 3 sigma, there is a upper control limit, mu plus 3 and standard error, that means sigma by root n, and mu minus 3 sigma by root n, that is also standard error. So, here you have got between these two limits 99.73% data comes, and that is why, because this is a theory that in normal distribution between plus minus 3 sigma limit 99.73% data will lie. So, therefore, these are control limit. So, I mean to say that suppose you wanted to tell about express delivery person, then in that case what you have to do, that instead of plotting the individually what happens, you make the samples, and sample wise you see the time. Okay. That means you can take the 5 times together and then take the average of that. Okay. So depending on this one, we make X bar and R charts. So in the X bar chart, record the measurement of K samples of size N. Typically N is 5, okay, that means size is generally kept 5 and K is at least 20, that means we measure 20 samples. For each of the K samples, record the mean Xi and then find the range of each sample, which is very easy, largest minus smallest value of each sample, that is I is equal to 1 to K, and calculate the overall average X bar and the average range R bar, as X bar is equal to sigma I is equal to 1 to K Xi by K, and this R is equal to sigma Ri, I is equal to 1 to K Ri by K. So you get a lower control limit X bar minus A2 R. A2 is a something, this is from statistical table you have to take. This is a type of coefficient, and UCL is equal to X plus A2 by A2 multiplied by R. So this A2 etc. they can be taken from tables. Such tables you can take from the books and handbooks. N is equal to 2, A2 is this much, and similarly these are other constants also, I just have written, but A2 value you have taken from here. Similarly, plot the X bar chart with LCL and UCL, central line and subgroup means. This central line has a magnitude of the overall average X bar. This line represents the desired average. Similarly, you can find out for R chart, you can plot the mean R and you can have lower control limit, that is D3 into R, and upper control is D4 into R, and D3, D4 can be taken from the table. Plot the R chart with LCL, UCL and central line and subgroup range Ri, that means in each group of 5 items, what is the range? So this central line has a magnitude of average range R. This line represents a reliable estimate of the range R. And sometimes you can even find out the standard deviation also chart. So standard deviation also can be done, and in fact empirically it can be calculated from range. Sigma is equal to R by D2. If you know the range, average range divided by D2, you get this one, and D2 again is given in the table. Okay. So suppose we want to construct the X bar and R chart for 20 sets of diameter of a piston head. The data is collected from 3 different measurements. The average of 3 measurements are that. Suppose this is the average of 3 measurements. Okay. These are the averages of 3 measurements, and like that we have got basically 20 sets of diameter. These are the 20 quantities. Okay. So that means total 60 measurements I have done. Then the ranges for each case, that this is a group of say suppose 3 things. Okay, so this is 0.00, this is 0.005, like that we have done. So now overall grand mean you can find out X is equal to 2. That means you add these 20 quantities and divide it by 20, you get this much. And similarly you add all these ranges and average range comes out to be this much. So from the table corresponding to N is equal to 3, A2 is equal to this much, D3 is equal to 0, D4 is equal to this one. So lower control limit for X bar chart, X bar minus A2R, 2 minus this much, you get this. And similarly you find out the upper control limit, that is X bar plus A2R, and this is equal to 2.005. Okay. Similarly, you can find out lower control limit, that is D3 into R, and this is becomes 0, and upper control limit for range comes out to be like this. Then you can plot this in X bar chart. This is X bar chart because average. So X bar chart and this is R chart. So here in X bar chart, this is the average X bar is 2, but these are the basically in subgroups you got this type of average values, so you are getting that, and upper control limit is this, lower control limit is this. So control limit is drawn. Now everything is within control limit. In case you find out that someday you do that this type of control limit is established, but someday you do some experiment and you find that value is this, more than the upper control limit, then naturally that means there is some assignable cause, you have to take corrective action. If it is within this, that is random fluctuation. Same thing about the variance range also, that range is coming like this, this is the average range and this is LCL and this is UCL, and here I am plotting that basically range for each this one item. This is range, this is range, this is range, this is range. So this is what that you do that. Now we can do that similarly. Instead of X bar and R chart, we can have X bar and S chart, standard deviation. Instead of range, you can use standard deviation, but generally it is preferred to use it when sample size is more, say n should be greater than 10. It is more precise, but more calculation needed. Then this is the control chart for variable. Similarly, we can have control charts for attributes. Okay. Control charts for attributes are essential for those quality characteristics that cannot be measured. For example, that cannot be measured physically, but such characteristics can be classified into one or two classes, usually defective or non-defective. For example, the presence of holes in an aluminum sheet classifies the item as defective. So we say, okay, hole is present or not present. When the quality characteristics of an item is measured by attribute, a control chart based on the fraction defective can be used. For example, in a process running with 2% defect rate, a mean of 2 defects per sample requires a sample of at least 100 for recording purpose. Okay. So this is, we can have this one. Calculation of control limits for attributes depends on two factors: whether numbers for constant size or proportions are being plotted. You can plot either numbers or proportions, and whether defective items you are considering are defects. There is a difference between defective items and defect. Defective item means it is either the item is defective or not defective. That means there may be one defect or two defects. But in defects, we are measuring the actual number of defects. Okay. So an item is considered to be defective if it fails to meet a required standard due to presence of one or more defect, whatever is that. Thus, there are two types of control charts for defective items based on whether the sample size is varied. Suppose sample size is varied, then P chart is better. Otherwise, you can have NP chart also. That means N you can multiply it by sample size. Also, based on the presence of defects, charts are constructed for varying sample size. That means you can have a U chart or you can have constant sample size. That means C chart. So, if talking about P chart, now the P chart is used for process control of defectives when it is not possible to take a sample of constant sample size because the size of samples are varying with time. Typical examples include arrival of mails in post office without the pin code number, scratches in glass sheet, holes in casting, like that. In such a situation, the control limits are drawn for the average frequent fraction defective, P bar. So P is actually P is number of defectives in each group divided by number inspected, and P bar is the total number of defectives during period and divided by total number of items inspected during period. Okay, so total number of defectives found divided by total number. So we can find out lower control limit P bar minus 3 sigma. So here 3 under root P 1 minus P by N, similar to work sampling type of equation, and UCL is P plus 3 under root P 1 minus P bar by N. If the calculation of lower control limit yields a negative quantity, then LCL is treated as 0 because a negative limit on fraction defective doesn't make sense. Okay. Similarly, by the way, UCL is coming more than 1, then naturally you have to take 1 only, it cannot be more than 1. So now example, suppose we have got serial number up to 20 and number of sample size in each case was, say, let us say 50, and I took 50 samples, somebody took 50 samples. In one sample he got 2 defect, in another got 3 defect, then 4 defect, sometimes he got 7 defect also, like that. So the first fraction defective is 2 by 50, that means 0.04, okay, because 2 by 50. So other values are that 3 by 50, that means 0.06, 0.08, up to this much he has done. Here that this is 7, so 7 by 50 is 0.14, this is what he has got. So then he can find out P bar, that means average defective. Total number of defectives during that period is 40. If you add these quantities, total will be 40, but the total number of items will be 20 into 50 because 20 samples were measured. and each one took 50, that each one size was 50. So 20 into 50. So this comes out to be 0.04. So therefore lower control limit is 0.04 minus 3 under root this much. So this comes out to be some negative quantity. So therefore it will be made 0. And upper control limit similarly comes. In upper control limit, instead of 0.04 minus, I will make it plus, other thing will remain same, and UCL will come 0.124. So it is observed that the fraction defective of 17th point is 0.14, which is more than the upper control limit. So that means this was outlier, this should not have been considered, okay. That is means there must be some assignable cause. So what we do that, hence this subgroup having 7 defective can be discarded, and you can have P is equal to 40 minus 7 because there was 40 defects in total in all the samples. So you minus it, but now the total number are inspected will be 19 into 50, okay. That group is discarded. Instead of 20 into 50, now you have 19 into 50, and this becomes 0.0347. So therefore now the lower control limit will be updated, lower control limit will be 0.0347 minus 3 and under root this much 0.047 P into this one. So this will be 0.0347, okay, this is 347, okay, this is equal to this. So again this is, suppose it is coming negative, so this is and then upper control limit comes here, okay. 0.0 formula is actually this one, this under the square root, it is P bar 1 minus P bar divided by N. So N is the sample size 50, P bar is 0.0347 and bracket 1 minus 0.0347. So anyway, so for NP chart we can also plot. In NP chart, instead of center line will be, instead of P, it will be N into P, and this is what, that this becomes N dot P, and upper control limit will be N into P bar, that NP bar is equal to 3, and this will be NP 1 minus P, and lower control limit will be NP minus 3 under root NP, this one. If you multiply whole thing by N, so this will go N square inside, so N square, this N will cut and this N will come here, okay. So that's why this one. If LCL is smaller than 0, set LCL is 0, and this is the thing. Similarly, you can have C chart. C chart means number of defects, okay. Suppose particularly if you are purchasing the cloth, so in 1 meter square area, how many defects are there? So here CL is equal to C bar, C is equal to sigma Ci by N, Ci is equal to number of defects in the ith sample, and N is equal to number of samples, how many samples you took, okay. So this is the number of defects basically, not defective, okay. Upper control limit formula is UCL is equal to C plus 3 under root C, and lower control limit is LCL is equal to C minus 3 under root C. So if LCL is smaller than 0, it is set to 0 since the count of defects cannot be negative. So here this type of thing is mostly that, suppose you are purchasing some cloth, okay, it is big cloth, it comes in a big thorn type thing, it is coming in a long that one. So you can have, it's not that it is defective or not defective, rather it is something in 1 square meter area. If there are, you find out some this one defects, some maybe small hole or whatever is that thing. So these, suppose there are 4 that some problems, okay, then we say that number of defects, so basically C will be called 4, okay, like that. Similarly, you can have another sample, another 1 meter square cloth you take, and here at the corner you find some defect, so here C is equal to 1. So it will be based on that type of situation, okay. So this is about, so like that we make a control chart, and through control chart we decide whether the process is under control or not under control. If your online data when it comes, if it crosses the boundaries of upper control and lower control limit, then you get alert that something is happening. Otherwise you think that okay, whatever be the way, due to random thing, that things are under control, and that is what the importance of a control chart. It gives you correct amount of feedback and it helps you to control the basically process. Okay, so only this much for today. We will continue lecture later on. Okay, thank you very much.